So we're ready to classify the possible Dinkin diagrams. So really the question comes down to finding the graphs built out of nodes and these types of edges such that they can be realized by a set of linearly independent vectors, so one for each node in the diagram. So these are vectors in the r-dimensional space that satisfy the appropriate angles between these simple roots. We have derived these angles a couple of weeks ago, and also that their lengths are given by the appropriate ratios. So if two nodes are not connected by an edge, then these vectors should be perpendicular to each other. If they're connected by a single edge, then they should have a 120-degree angle and should be of equal length. If they're connected by a double edge, then one is longer by a factor of square root of 2. So the one on the arrow is pointing from the longer to the shorter one, and the angle is 135 degrees. And then with a triple edge, we have an angle of 150 and a length ratio of square root of 3. So what we're going to do is we're going to go through a series of lemmas that make the allowed Dinkin diagrams more and more restrictive. So the first step we're going to take is going to look at Dinkin diagrams of rank 3, so meaning graphs with 3 nodes. So let's look at how they may look like, and we're only interested in connected diagrams for the moment. So the simplest graph I can draw is this one. We can also have a double edge. Perhaps we can have 2 double edges. We can have a triple edge in here, maybe a single edge. But of course we can also have a triangle type graph. So let me not really draw all possible graphs one can build with these edges. I mean, I can always turn one of these single edges into double or triple edges. But let's just look at what happens for these particular ones. So an important point is that grab another color. When is such a graph a Dinkin diagram? Well, precisely when I can find vectors in R3. This is R3. So 3 vectors there. Maybe something like this. That satisfy these angle requirements. But we know something particular about vectors in R3. So if we look at the 3 different angles that one can form between 3 vectors, let's denote them theta 1, theta 2, and theta 3. Then what do we know about such angles? Well, we know that if they add up to 2 pi, then really these vectors are going to lie in a single plane. Right? If the vectors are in a single plane, then of course they add up to 2 pi. But the converse is also true. But this we do not allow, right? Because we want our roots. So this is alpha 1. Let's put the index up here. Alpha 2, alpha 3, to be linearly independent, so we're not allowed to be in a plane. So any linearly independent set of 3 vectors, it always satisfies that the sum of the angles is smaller than 2 pi, or for my purposes, it's actually useful to use those regular degrees, so it has to be smaller than 360 degrees. So now we can just check for these types of diagrams whether they actually satisfy this. And if they don't, then they cannot be Dinkin diagrams. So let's do the calculation. So here, in this case, I have to look at all pairs of points. So if I look at the outer two, they are not connected by an edge. So their angle is 90 degrees. 90. And then the first two are connected by an edge, so it's 120. And then the second two are also connected by an edge. So if I add these up, this is 330 degrees. So it certainly satisfies this bound. So this is an okay Dinkin diagram. So how about this one? So now I have 90 for the outer two, 120, and then 135. So that gives me 345 degrees total. So that is fine too. Here I have twice 135 plus 90. So that's 360. Here I have 150 plus 120 plus 90. So that's also 360. And here I have 3 times 120, so this is also 360. So none of these actually satisfy this bound. Well, let me get another color. So this means that these are not valid Dinkin diagrams. And note that if I would add any more lines to these edges, that would only increase the angle, so it would violate this bound even further. So we really only have 3 possible Dinkin diagrams of rank 3, because I can put the arrow in this edge in both directions. So this is lemma 1, so let me write the result. There are exactly 3 Dinkin diagrams of rank 3, and they're exactly these ones. And all other graphs on 3 nodes are not Dinkin diagrams. Or they're not connected, so they do not correspond to compact, simple Lie algebras. So this would turn out to be a very useful property if we look at graphs with more nodes. And the reason for this is that whenever we have a a graph with more than 3 nodes, one can always look at a subgraph there. And if the original graph was a valid Dinkin diagram, then the subgraph is going to be 2. So any subdiagram, so I'll define in a moment what I mean by that, of a Dinkin diagram is also a Dinkin diagram. So by a subdiagram I really mean a subset of nodes together with all the possible edges between them. All edges between them. So here's an example. Let's look at the following diagram. Maybe something like this. So I have 2 double edges and 2 single edges. And let's look at the subset corresponding to these 3 vertices, nodes. So why would this subdiagram, so that would correspond to this diagram, here. I mean, if this were a Dinkin diagram, why would this also be a Dinkin diagram? So let's see. So what does this mean? This means that we have 4 vectors in R4. So we've singled out 3 of them. So this is in R4 that are linearly independent, and their angles and relative lengths are specified by this. But that means that if I select just a subset of those vectors, then they are also going to be linearly independent. Right, so I have now 3 vectors. Okay, they live in some 3-dimensional hyperplane in R4. So okay, I can just look at this 3-dimensional plane, so then these become vectors in R3. They're linearly independent, and of course the lengths and the angles have not changed. So the edges between these 3 vertices here, they are the same as in the original graph. Okay? So why is this useful? Well, so this says if this is Dinkin, then the subgraph is Dinkin. But this is equivalent to saying that if this is not Dinkin, and in this case it really is not, because we know this is a rank 3 graph and it's not in this list, so this is not the Dinkin diagram, then that implies that this larger graph is also not Dinkin. So whenever you can find in a larger graph some subgraph of say 3 vertices that is not this one, then it's not a valid diagram. So in particular, what can we deduce from this? Well, for instance, there are no rank 3 Dinkin diagrams that have a triple line. So that means that even in larger graphs, there cannot be a triple line, because otherwise I could find some subgraph that has the triple line in there, and it would give a graph which is not a Dinkin diagram. So a direct consequence of this is that the triple line really can only appear in a rank 2 diagram. So the only Dinkin diagram with a triple line is really the rank 2 Dinkin diagram corresponding to G2. So the exceptional Lie algebra of rank 2. Okay, so really we only have to focus from now on single and double lines. And here is another trick we can use, and that is that whenever we have a graph, we can not only make it smaller by taking a subdiagram, but we can also make it smaller by contracting an edge. And then the similar thing holds. So in try it like this. So contracting a single line in a Dinkin diagram gives another Dinkin diagram. So let's look at an example. So suppose I take, let's see which one. No, let's do something like this. And let's contract this particular edge. So that is going to give a graph that is now a triangle. Like this. So why is this going to give a... so why, if we can find linearly independent vectors alpha with these angle and length requirements, then I can find similar one less vector satisfying this? Well, if I denote here this vector, so the simple root by alpha and a beta, so I will have 4 vectors in this case, alpha hat, beta hat. So this will be in the rank R dimensional space. Since they are connected by a single line, they will have equal length and 120-degree angle. So what is going to be the corresponding then set of simple roots for this diagram? Well, simply we take all the roots as before, but we replace alpha and beta by alpha hat plus beta hat. So I get now one less vector. Since these have 120-degree angle, this will again have the same length as alpha and beta. So the only thing one has to check now, so certainly, I mean, these are going to be linearly independent if these were. What we can check is that the appropriate inner products are maintained here. So suppose I look at the inner products of this particular vector with alpha plus beta. So we know that those inner products, at least if I take the ratios, they are encoded in the Cartan matrix. So I would have to check that, for instance, the inner product of gamma with alpha plus beta divided by, let's say, the norm squared of alpha plus beta. So this is one of the entries in the Cartan matrix, and it has to correspond to a single edge. But we can easily compute now that if gamma is connected to alpha, then it cannot be connected to beta, because otherwise we would have a triangle like this. So gamma is going to be orthogonal to beta. So this is just gamma dot alpha. But I said that the length of alpha plus beta is the same as the length of alpha. So this is just alpha squared. Right, but this was necessarily given by the corresponding edge. The fact that this is a single edge, the value here is the same as there. So this is also going to be a single edge connecting gamma with alpha plus beta. So we can really check that this particular operation, it preserves all possible inner products between vectors that are not corresponding to this node and this node. So again, why is this useful? Well, if contracting any edge in a Dinkin diagram gives a Dinkin diagram, then the converse of this statement tells us that if this is not Dinkin, and in this example indeed it is not Dinkin, then this is not Dinkin either. So let's see a consequence of this. The first consequence is that a Dinkin diagram has no loops. So why is that? Well, let's just look at an example. Suppose I have a loop like this. So this could be a possible graph. Then I can simply contract some edges on this loop to turn it into a triangle. So contracting here, for instance, this edge gives this graph. But this one has a subgraph that is a triangle, which is not allowed. Right. And in general, you will always have a single edge within a loop, because what is the other only possibility? It is that I have, say, a loop consisting just of double edges, but then there will be double edges next to each other, and also that is not allowed by the first property. So this helps already a lot, so we cannot look at Dinkin diagrams with loops, so they're always going to be trees. So then the next observation one can make is that a Dinkin diagram contains at most one double edge. And here the reasoning is the same as before. If we would have more than one double edge, so suppose I would have something like this, then I can always contract the single edges that separate these two until these double edges become adjacent to each other. But this is not allowed. This is not an allowed configuration. Let's continue. So there are a couple more lemmas to do. So there is another type of contraction one can do. If a Dinkin diagram has two dangling edges next to each other, then they can be merged into a double edge or a double line. So what do I mean by this? So if I have an arbitrary diagram like this, which has some vertex, some node, on which there are two of these dangling single lines, then what I do is I replace it by a double line like this. And the reasoning of why this is allowed is similar to here. So if I have vectors alpha and beta corresponding to these, then I replace them by the sum alpha plus beta here. And you can easily check that if you then take the inner product, say with this vector gamma here, then these inner products are exactly going to be of the right form. For instance, one thing you can see here is that these are connected by single lines, so alpha should have the same length as gamma, which should have the same length as beta. So that means that if and alpha plus beta, or alpha and beta, are perpendicular to each other. So the length of alpha plus beta is going to be square root of 2 times the length of gamma, or the length of alpha. So it's square root of 2 larger than the length of gamma, so this agrees with the fact that there is a double line here pointing towards gamma. Okay. So let's draw a consequence again. So this is lemma number 8 already. A Dinkin diagram has either one double line or one junction of the following type, or none of these. And it cannot have both a double line and a junction. So here I really mean a node that has exactly 3 lines coming out. So let's see why this is the case. Again, using that we can merge these dangling single lines. So suppose we have 2 of these junctions, so that would look like something like this, if you like. Maybe there is another one here. So what I can do is I can contract some of the edges to bring this to this form. And then, so this is using the contraction, so 4. And then I can merge using 7 both these pairs of dangling edges, and I would get something like this, with 2 double edges that are adjacent to each other, but that is not allowed. Similarly, if I would have a junction as well as a double edge, I could contract this edge and merge those two, and then again produce this configuration, which is also not allowed. Okay. So let's see what the remaining possibilities are at this point. Okay. So the remaining possibilities are the following ones. We can have just a line of single lines of arbitrary length. We can have something with a junction, so something like this with any number of nodes on these 3 lines. I could have a double edge with kind of single lines attached on both sides. Some arrow here. And then, okay, what are the other options? So I've exhausted now these 3 options, so really the only thing that they have not included is this rank 2 triple line. So this is really all we can do. But even within these classes of graphs, some are not allowed. So here are some exceptions. So this is the last lemma. It says that the following diagrams are not Dinkin. So meaning that one cannot find linearly independent vectors that satisfy the appropriate inner products. So let's see which are these. I don't want to make a mistake, so let me check. In the case of the junction, I cannot have this rank 7 object. I cannot have this, so now there are how many? 5 of them. 1, 2, 3, 4, 5. And this one really has to study on a case-by-case basis. And in the exercises, you're going to check, I think for this particular case, that one cannot find vectors that satisfies these angles with each other. And the basic idea is that for each of these graphs, you can find a linear combination of these vectors that necessarily has to vanish when you work out the inner product, or the norm of this linear combination. But from here we're essentially done, and we can conclude. So here's the theorem. The Dinkin diagram of any simple compact Lie algebra is in the following list. So let's nicely group them up. So the simplest possibility is having this line. So we have an arbitrary number of lines here. So the other possibility is that we have a double edge. So certainly if we take one of these branches to vanish, then they're never going to have one of these subgraphs. So that means that they're allowed. So I can take any number here of single lines, and then what order? Yeah, double edge like this, or I can orient the double edge in the other direction. Okay. Now let me mention here also the triple line. What other options do we have for the double line? Let's see. So we cannot make both of these branches of length 2 like this, but we can put one edge on either side. But I cannot add another one on this side, because then it would contain this subdiagram. And I cannot add another one on that side because then it would contain this one. So these are really the all possible diagrams that contain a double edge. So now it remains to look at the diagrams that have just a junction. So here is one possibility, an arbitrary number of single lines followed by this one, because it does not contain any of these three. And then there are only a couple that we have missed. So let's see. We can do this. Right? This contains none of these. I can extend this branch a bit. I do something like this. I cannot extend this branch because then all of these branches would have length at least 2 and contain this one. I can also not extend this one any further because then it would contain this one. So the only thing really I can do is extend this one by another edge. So I get this. Okay, and that is all, because I cannot extend this one any further because it would contain that one. So we're done. So these Dinkin diagrams, they have received some names. These are called, these infinite sequences are called AN, BN, CN, DN. This we've already seen is G2, F4. So notice the indices are all the rank, right? N is the rank in this case. So the number of nodes. Here I have E6, E7, and E8. Okay. So do they really exist? These Dinkin diagrams, are there Lie algebras that have these Dinkin diagrams? The answer is yes, and actually we know all of them on the left hand side from our introductory video on the Lie groups. So this here is simply the special unitary group in n+1 dimensions. This one is the orthogonal group in odd dimension. This is the compact symplectic group, SPM, that we only very briefly looked at. And then these are the orthogonal groups in even dimension. And this list of 5 remaining groups are called the exceptional Lie algebras. And they really do exist. So one can actually construct the corresponding Lie groups. And in the exercises you're gonna figure out, for instance, what the dimensions of a couple of these Lie groups are going to be by constructing the corresponding roots or root system. Because remember, the dimension of a Lie group is the number of roots plus the number of Cartan generators. So the rank of the Lie algebra. Now, if you look at this list for small n, then you'll see that, I mean, it's not exactly mutually exclusive. And indeed there are overlaps here, and some of them we've already encountered before. So we have, for instance, for the rank 1 Lie algebras, so that is SU2, it is really the same as SO3. And it's also the same as the compact symplectic group of rank 1. So that means if we want to make this this list complete and without overlaps, we can take here n to be larger or equal 1. Then SO3 is already contained in here, so here I should take n larger or equal 2. But one should also notice that here the compact symplectic group corresponding to C2, it's the same as B2. So SB2 is really isomorphic to SO5. So I only want to start this one at n larger or equal than 3. And I'm finally looking at D3, so that corresponds to taking just these 3 vertices. Well, that is exactly the same as taking A3. So this is saying that SO6, special orthogonal group in 6 dimensions, is really isomorphic to SU4. So we actually just want to start here at n equals 4. Well, with these bounds on n, this is really an exhaustive list without overlaps. So in the last video we're going to see whether knowing something about all possible compact Lie algebras can tell us something about possible extensions of the gauge group in particle physics.